All right, well, welcome back. Finished off with chapter 1, moving on now into chapter 2. Topic-wise, we're going to shift gears a little bit into chapter 2. We want to start talking about atoms, ions, and then into molecules. We'll define some of those terms as we go along here. But starting out, an atom is this smallest unit that maintains all of the properties of individual elements. So we want to think about what we can understand about the underlying structure of an atom, how that's going to relate to the way we describe some of the properties of an atom, and how we can use that to kind of extend some of the things we want to calculate out. So in terms of atomic structure, we're going to look at three basic subatomic particles that are present in an atom, and those are going to be neutrons, protons, and electrons. Right? And each of these are important in understanding some properties of atoms, but also in terms of chemistry and how chemistry is going to happen when atoms start to kind of mix together or interact with each other. Now, neutrons and protons are located together in a part of an atom called the nucleus. Right? And the main difference between neutrons and protons is that neutrons have a neutral charge and protons have a positive charge. So I'm going to put a positive right here. And over on the side here, I'm going to draw sort of a cartoon version of an atom. Atoms are a lot more complicated than the way we're going to describe them. But basically, you've got a nucleus in the center. This is where all the neutrons and protons are. And then surrounding the nucleus is what's called an electron cloud. And this is where that third particle comes in, the electrons. Now, electrons, you might imagine, have a negative charge, since we've seen that protons have a positive charge. Electrons live in this cloud surrounding the nucleus. Right? And you may have heard it said before that atoms are mostly empty space. That's basically true. Electrons are vanishingly small. And in fact, the scale here on my drawing is way off. The nucleus is a tiny speck of material in the center of an atom. Yet it's where almost all the mass in the atom resides. So we'll see that neutrons and protons are significantly heavier than electrons, about 1,000 times heavier for each one. So you have almost all of your mass here in the nucleus, but then you have this very large area relative to the nucleus where the electrons are kind of moving around. So most of the atom is empty. Now, in terms of what does this tell us about atoms, and in fact, we're going to be talking about the periodic table. So I'll be referring to the periodic table occasionally through the lecture. So I'm going to reference where some of this information shows up on the periodic table. Now, in terms of subatomic particles, what we want to know about any particular atom, one thing is its atomic number. Now, definitionally, atomic number is the number of protons in an atom. Right? And you could say in the nucleus of an atom because that's where the protons are. Now, in terms of the periodic table, whenever we see an element described, there will be a kind of a rectangular box like this. Symbol for the element is in the center, so I'm going to use carbon as an example. The atomic number of every element generally is located above the symbol. So for carbon, the atomic number is 6, and that represents that a carbon atom has 6 protons in its nucleus. Right? The atomic number, or the number of protons, is what defines the identity of each individual element. So this defines element's identity. So an element that has, any atom that has 6 protons is a carbon atom. It's a part of the element carbon. If you take away a proton somehow, and now there's only 5 protons, it's not a carbon anymore. Now it would be an atom of boron. Okay. The mass number, another thing we want to know about an individual atom. This is the number of protons combined with the number of neutrons. Right, so we said both of those are in the nucleus. We combine all the particles in the nucleus, right? Combined, those are nucleons. We add those together, and that is the mass number. Now, the mass number doesn't directly appear on the periodic table. If we want to know the mass number, we either have to figure it out from other components of information, or we have to be given it when a particular atom is being described. And the way the mass number is shown is as a superscript located before the element symbol. So if I write a 12 here as a superscript before the carbon, that would be read as carbon 12. This would be an indication that the mass number of this carbon atom is 12. Now, as we mentioned before, carbon has 6 protons, so this atom has 6 protons, and if we took the mass number and subtracted the number of protons, that would leave 6 neutrons as well. Now, one of the reasons the mass number doesn't appear on the periodic table is because there isn't only one option for the number of neutrons, right? There's only one option for the number of protons because that's what defines each element. But we can also have a carbon atom that happens to have a mass number of 13. So this would be carbon 13. And we know it's got 6 protons. That comes with identifying it as a carbon. But in this case, there would be 7 neutrons in this particular nucleus, resulting in a different mass number. So the number of neutrons, which contributes to the mass number, can be variable, right? It isn't always variable, but it can be variable. And because of this variability, we have this concept or this idea of atoms that are isotopes of each other. So isotopes are atoms of the same element. So I say same element, that means same number of protons, right, that have different mass numbers. So having a different mass number, if you have the same number of protons, implies that you have different numbers of neutrons. That would be another way you could define the term isotope as same number of protons but different numbers of neutrons. And the 2 examples of carbon that I described would be classified as 2 isotopes of the element carbon. One with mass number 12, one with mass number 13. There is another naturally occurring isotope of carbon with a mass number of 14. So that would have 6 protons in the nucleus and 8 neutrons in the nucleus. Now, some combinations of protons and neutrons are stable. Carbon 12 and carbon 13 are perfectly stable elements. Carbon 14, however, is not a stable element. Carbon 14 is actually radioactive. It decays, and carbon 14 will actually decay in a way that turns it into nitrogen 14, and that's actually a very useful tool for dating something like an archaeological sample. And if something is alive, it is exchanging carbon with its environment. So a plant, for instance, is pulling in carbon dioxide from the atmosphere. So while it's alive, it's constantly replenishing its carbon that's in its structure from natural sources. So there's a set amount of carbon 14 in there. Once that plant, if say it is a plant, a tree maybe, once the tree dies, it stops exchanging. It stops pulling in carbon anyway. It's still going to release some carbon. But that almost starts a timer. As the carbon in that maybe wood structure starts to decay, the amount of carbon 14 will go down over time, and it goes down in a way that if you can carefully measure the amount of carbon 14 remaining in that sample, you can get a window of how old that material was. Like, when did that tree die? If it had been made into, say, the shaft of an arrow or something like that, you might be able to date when that arrow was actually used by the person that made that arrow. Okay, I think we'll stop right there, and we'll pick up the example in the next video.